Hello everyone, welcome back to my channel. So in this video we are going to see demodulation of DSB SC signals. Okay, so demodulation of DSB SC signals. So there is only one method for demodulating DSB SC signal, that is synchronous detector. Okay, synchronous detector. Synchronous detector is the detector circuit which is used to demodulate DSB SC signals. Okay, so the block diagram of this synchronous detector. So I always have told you for demodulation input will be the modulated signal, that is Dsbs SC modulated signal is the input, and the output will be proportional to the message signal m of t. And the filter, the type of filter which we use will be low pass filter. Okay, so the type of filter which we use will be low pass filter. Right, we'll see the block diagram now. So this is product modulator, so for which one of the input will be AC cos 2 pi FCT, that is carrier signal, the same carrier which we use at the transmitting end. So local carrier, local oscillator generated carrier. Okay, so local oscillator generated carrier whose frequency is same as the frequency which we use at the transmitting end. So the other input will be S of t of DSB SC. Okay, so input will be modulated signal. Okay, so S of t of Dsb SC and local oscillator generated carrier whose frequency is same as the frequency which is generated at the transmitting end. Okay, so the output is then passed through a low pass filter. The output is then passed through a low pass filter, then we'll get the output. So V naught here is proportional to m of t. Okay, so let the intermediate output of this product modulator be Z of t. So product modulator multiplies the two input signals. Okay, so it just multiplies the two input signals. Right, so when it multiplies the two input signals, so what is the output of this Z of t? So Z of t is one input is S of t of Dsb SC and the other input is AC cos 2 pi FCT. So other input is AC cos 2 pi FCT. So Z of t is equal to S of t of Dsb SC. So this is one input multiplied by AC cos 2 pi FC into t. So we know that S of t of Dsb SC is given by AC cos 2 pi FCT into m of t, that is Dsb SC modulated signal is this. This is multiplied by AC cos 2 pi FC into t. So it will be AC square m of t into cos square 2 pi FC into t. Okay, so this is equal to AC square into m of t into, so cos square 2 pi FCT can be written as 1 plus cos 4 pi FCT divided by 2. 1 plus cos 4 pi FCT divided by 2. So this is Z of t. So this signal Z of t is passed through a low pass filter. Okay, so it is passed through a low pass filter which has the cutoff frequency of W, which is equal to the message signal frequency. Okay, so all the frequencies around message signal will be passed and all frequencies above message signal which are very much greater than message signal are going to be rejected by this low pass filter. So the output of low pass filter, is so the output is V naught, which is equal to, so if you observe first term is AC square by 2 into m of t. So m of t is the only signal and its bandwidth is W, so it is passed by the low pass filter. So AC square by 2 into m of t, and the second signal is multiplied by cos 4 pi FCT into m of t. So m of t into cos 4 pi FCT. So the frequency here is W and the frequency here is 2fc, so it is 2fc plus W, which is very high frequency. So this term is eliminated by the low pass filter. So this cos 4 pi fct is eliminated by the low pass filter. So the output of low pass filter is only this. So this is just a scaling factor, so V0 is proportional to m of t. So V0 is proportional to m of t. Thus we can say that a Dsbs signal can be demodulated at the output of this synchronous detector. That is, output is proportional to the message signal. Okay. So now we will consider a special case. Okay. So we will consider a special case in synchronous detection of Dsbs signals. So the special case is if there is a phase difference. If there is a phase difference of phi, if there is a phase difference of phi between the carrier used at transmitter end, and local oscillator generated carrier. So in this case, what will be the output? We have to check. So I'm drawing the same block diagram of this synchronous detector. So this is product modulator, and output of product modulator is given to low pass filter. So this is V0 and this is Z of t we have taken as it is. So this is now local oscillator generated carrier. So this is the Dsbs signal. So what does this mean is, if the carrier used at the transmitting end is AC cos 2 pi fct, that is what we are taking, and the local oscillator generated carrier, that is here. So the local oscillator generated carrier here is AC cos of 2 pi fct plus phi. If there is a phase difference, that means phase difference of phi means AC cos of 2 pi fct plus phi. So if there is a phase difference of phi between local oscillator generated carrier frequency and the carrier used at the transmitting end, that is, this carrier is used to generate the Dsbs signal, but in order to demodulate we are generating some local oscillator carrier here. If it contains a phase difference of phi, in that case what will be the corresponding output of synchronous detector we are going to find now. Okay, so this is the special case. So Z of t is given by S of t of DSB SC now multiplied by AC cos of 2 pi fct plus phi, because there is a phase difference of phi. Okay, so this is AC cos 2 pi fct into m of t, yes or no? So this is at the modulator end. So at the modulator we are using this carrier AC cos 2 pi fct into m of t. This is multiplied by AC cos of 2 pi fct plus phi. Okay, so AC into AC becomes AC square into m of t taken common. Okay, so I am dividing by 2 and multiplying with 2 cos of 2 pi fct plus phi into cos of 2 pi fct. Okay, so this is of 2 cos form. So cos of a plus b, cos of a minus b, AC square by 2 into m of t into now tell me, so this becomes cos of 4 pi fct plus phi, cos of a plus b plus cos of a minus b, this becomes cos phi. So Z of t is equal to, I am writing it as two terms, AC square by 2 m of t into cos phi plus AC square by 2 into m of t into cos of 4 pi fct plus phi. Okay, so this is the output of product modulator. Now this output is passed through low pass filter. This is passed through low pass filter. So output of low pass filter is now. So if you observe here, the first term is AC square by 2 is a constant, cos phi. So cos phi is also a constant, cos of some angle is also a constant value. So all these are constants. Only the signal present is m of t, which is same as low pass filter cutoff frequency. So this term will be passed by the low pass filter. And if you observe here, the frequency here is W and the frequency here is 2fc, so it is multiplied, so addition in frequency domain. So here the frequency is 2fc plus W, which is very high frequency, so this term is rejected by the low pass filter. So output will be AC square by 2 m of t into cos phi. Okay, so this is the output of synchronous detector. Okay, so here when phi is equal to 90 degrees, when phi is equal to 90 degrees, then V0 is equal to 0, because cos 90 is equal to 0. So when phi is equal to 90 degrees, the output is becoming 0. So there is no output at the output of synchronous detector. So this effect is called as Quadrature Null Effect. Okay, so this effect is called as Quadrature Null Effect. Quadrature means 90 degrees phase shift. That is, if there is a phase shift of 90 degrees present between the carriers used at the transmitting end and local oscillator generated carrier. So if there is a phase shift of 90 degrees present between the carriers, then the output is becoming 0. Null means becoming 0. Okay, so the output becomes 0, and hence such an effect is called as Quadrature Null Effect. In short, we'll call it as QNE. Okay, so that is called as Quadrature Null Effect. Okay, so Quadrature Null Effect arises because of the 90 degrees phase shift between the carriers used at transmitting end and local oscillator generated carrier at the receiver end. Okay, so this is the special case. So in order to avoid this Quadrature Null Effect, perfect synchronization must be maintained between transmitter and receiver. So whatever the phase shift you have generated at the transmitting end, the same phase shift must be there at the receiving end. So therefore perfect synchronization is required between transmitter and receiver. So if the phase shift is there, if the phase shift is other than 90 degrees, then no problem, you will get some output. Okay, some scaled output you will get. So cos phi will be some value, so you'll get V0 again proportional to m of t. But the problem is only if you have a 90 degrees phase shift between the carriers used at the transmitting end and receiving end. Okay, so this is the special case of synchronous detector. Okay.